Chapter 7, Second Order, Differential Equations. Introduction. Chapter 7 explores the world of second-order differential equations, providing insights into their applications and solutions. It covers the difference between linear and nonlinear equations, introduces the superposition principle for finding general solutions, and discusses the concept of linear dependence and independence of functions. The chapter also explains the characteristic equation and its three cases, which are crucial in determining the roots that yield the general solution. Additionally, it delves into the topic of damped vibrations and how to incorporate damping forces into the differential equation. Learning objectives. By the end of this chapter, you should be able to 1. Understand the superposition principle and its application in finding general solutions to linear homogeneous differential equations. 2. Determine whether a set of functions is linearly dependent or linearly independent. 3. Solve second-order differential equations with constant coefficients using the characteristic equation. 4. Identify the three cases of the characteristic equation: distinct real roots, a single repeated real root, and complex conjugate roots. 5. Apply the general solution to real-world problems involving second-order differential equations, including damped vibrations. Key points. The superposition principle states that any linear combination of solutions to a linear homogeneous differential equation is also a solution. Linear dependence of functions occurs when there exist constants, not all zero, that make their linear combination equal zero for all x over the interval of interest. To find the general solution to a second-order differential equation, it is necessary to find two linearly independent solutions. The three cases of the characteristic equation are distinct real roots, a single repeated real root, and complex conjugate roots. Damping forces can be incorporated into the differential equation for spring mass systems, resulting in damped vibrations. Real-world application. One real-world application of second-order differential equations is in modeling the motion of a mass spring system. For example, when a mass is attached to a spring and set into motion, its position can be described by a second-order differential equation. By solving this equation, we can determine the motion of the mass and predict its behavior over time. This has practical applications in fields such as engineering, physics, and robotics, where understanding the dynamics of mechanical systems is crucial. Additionally, the concept of damped vibrations is relevant in designing systems that minimize unwanted oscillations and ensure stability. Conclusion. Chapter 7 delves into the world of second-order differential equations, providing insights into their applications and solutions. By understanding the superposition principle, linear dependence, and the characteristic equation, you can find general solutions to these equations. These concepts have real-world applications, such as modeling the motion of mass spring systems and designing systems with damped vibrations. By mastering the material in this chapter, you will gain the skills to solve a wide range of second-order differential equations and apply them to various real-world scenarios.